Hello, my name is Kennedy Thorne, and this is Lab 2. In this lab, we had to take a video of an object slowly falling. The fall must be slower than that of a rock falling. I used a ball of socks. We used Tracker to track its position throughout the fall, and then we used GlowScript to find the computational data with gravity acting on the object, and then also with gravity and drag acting on the object. The purpose is to find the effect of drag and to explore Newton's second law into more depth. Now, drag is air resistance. It is the motion moving in the opposite direction of the object's motion. So this plays a significant role. Here are some useful formulas. The gravitational constant is 9.8 meters per second squared, which is a force acting on the object in the downward motion. Newton's second law is force equals mass times acceleration. The momentum principle is momentum equals mass times velocity. And then drag force equals the negative square root of the velocity of an object. Here's a video of me dropping the ball of socks. As you can see, as you track the position of the socks, it moves in the negative y-axis direction. To the right, you can see the y change in position over time as the object falls. Here's the ball of socks at the starting position. Here's the ball of socks at the ending position. As you can note, in the right corner, the graph has a negative slope, which shows that the object moves in the negative y direction. Here's my code where we pretend like gravity is the only force acting down on the object. Note, we had to make minor changes for the ball's mass, position, velocity, along with other formulas. The drag constant is 0 since we are pretending gravity is the only force. There's also a negative slope because of the object moving in the negative y direction. Compared to the tracker video, you can tell that this ball moves a significantly further distance in the same amount of time. Here's my code with both gravity forces and drag forces acting on the object. As the object falls, gravity pushes it down. However, the drag and the air resistance push the object upwards. As you can tell in this graph, the object didn't move nearly as far as it did with just gravity due to the drag force. To change this in my code, I had to create the drag force and then add that together with the regular force to create the net force. I also had to change the value of B to best fit the curve of the line we got from Tracker. On this slide, you can nicely see all three scenarios played out together. The orangish color at the bottom is the Just Gravity GlowScript code. As you can notice, it travels much further than the other two lines, while the other two lines tend to pair nicely. The tracker video data is in the grayish blue color, and then the drag and gravity GlowScript data is in the yellow color. This helps to confirm that there are multiple forces acting on the object, and it shows the effect of drag. In response to the lab questions, an object reaches terminal velocity in the simulation with drag when the drag force magnitude is equal to the magnitude of the gravitational force. As for the other question, the object's terminal velocity will be the same whether it is dropped or thrown down, but it will reach it much faster when thrown down versus when it's just dropped. Therefore, the time of achieving terminal velocity is the only difference. Some potential errors could come from the difficulty of tracking the object due to its fast motion. We just had to choose the center of the blur as the object fell. It was hard to tell the slope and adjust the drag value, which is b, and we just had to guess until it looked about right. Also, another potential error could come from the assumption that only gravity and drag forces are acting on the falling object, while there may be other forces in play. Some improvements could be to have a bigger object to track so it's easier, or to have a more secure space with limited airflow / other potential forces. Thank you and have a good day.